Hey everyone, my name is Kevin Uckles. I'm a graduate student at Princeton University with Professor Ali Yazdani. And today, my team and I have a new paper that will be posted on arXiv tonight called Quantum Textures of the Many-Body Wave Functions in Magic Angle Graphene. We're really excited to share these new results. Let me start by just showing you some kind of high-level results from this paper. We're using scanning tunneling microscopy to image Magic Angle Graphene devices, and we find that nearly all the correlated phases that we see, correlated insulators, superconductors, and pseudogap phases, all are isospin ordered. They're intervalley coherent ordered phases, which we can measure through atomic scale imaging of these states. So STM images of these states show that the graphene lattice unit cell is tripled, which is a smoking gun signature of intervalley coherence. We put this together, these atomic scale signatures that we see, as well as some Moiré scales textures that we observe in these devices, together with a newly introduced symmetry-based order parameter analysis, which I'll tell you about in this talk, to analyze a number of correlated states, but particularly with focus at nu equals plus or minus 2, these correlated insulators. And we find that many features of this nu equals plus or minus 2 insulator closely match predictions of incommensurate Kekulé spiral order as predicted in something like 2020, 2021. Finally, we find that the presence of IVC order is really ubiquitous. It's seen in all of these symmetry-broken states, but the exact type of IVC order that we see in these states is particularly sensitive to things like strain. Here I'm showing nu equals minus 2 insulators in moderate strain and an ultra-low strain device, which look completely different. And we see that it changes as a function of carrier density. As we dope this insulator into a superconductor, the presence of IVC order is still there, but the type of IVC order is very different. So all this will be discussed in this talk. I think I went a little over the 30 seconds that I had allocated for that, but that's okay. I promised to keep this kind of at a high level and really to gloss over many of the details to make sure that we cover all of the material in this talk. But I refer you for details to our preprint and particularly to some March meeting talks that we'll be giving as a team next week. So my colleagues Ryan Lee and Mengshil Oh, together the three of us will be giving March meeting talks on Tuesday morning. My advisor, Ali Yazdani, will be giving an invited session on Tuesday afternoon discussing this paper and many details that we can't include here. And then our close collaborator, Tomo Sejima from UC Berkeley, will be discussing the local order parameter analysis that I'll tell you about today from a symmetry point of view. So without further ado, let's talk about the role of symmetry breaking in Magic Angle Graphene. Magic Angle Graphene has these flat bands where correlation effects dominate, and the role of correlation effects is often to entice electrons to do everything and anything they can to mitigate Coulomb interactions. They want to break symmetry spontaneously in order to lower their energy and mitigate these repulsive interactions. And so this is all shown in a phase diagram that was first introduced to us by Pablo Herrero's group at MIT, where he sees at 2 holes per Moiré unit cell, they find this correlated insulator, and then when you dope to either side of this correlated insulator, they see this superconducting phase, which we now know to be unconventional. So at first, Pablo's paper labels this as a Mott insulator, which is a reasonable assumption given what we knew about this at the time, that it happened at half filling of a flat band, and it seemed to show very similar phenomenology to that we see in the cuprates, where in something like lanthanum, barium, copper oxide, we would see something like an antiferromagnetic Mott insulator and a D-wave superconductor to either side. So this was early understanding in this field, but more recent understanding from many authors, I just show one device from Andrea Young's group, showed that quantum oscillations can tell us a lot about this insulator and particularly point us towards a more symmetry broken nature to this insulator. So here we're looking at Landau levels as a function of both magnetic field and density, where you find a Landau fan from charge neutrality that has the entire isospin symmetry of graphene. So it has twofold degeneracy for spin and twofold degeneracy for valley. But as you dope the system, you find that this fourfold degeneracy kind of has a little bit of a crossover effect. And then once we hit nu equals minus 2, we find this robust insulator phase that Pablo discovered. And then we find emanating from this nu equals minus 2 insulator, a series of Landau levels with reduced degeneracy. So minus 2, minus 4, minus 6, these are the Chern numbers of those Landau levels, telling us that the Fermi surface upon which they impart is broken symmetry and likely extracts all the way back to zero field, where this is interpreted as a broken symmetry insulator. insulator. So I think this is one of the strongest reasons to believe that this is a symmetry broken insulator. Indeed, there were spectroscopic measurements from my own team and compressibility measurements that show signatures of symmetry breaking, where we find there's a resetting of the low energy excitations, possibly indicative of long range isospin breaking, possibly as a result of local isospin symmetry breaking. All of these results point to the fact that symmetry breaking, isospin symmetry breaking, is a really great starting point to understand correlated phases in magic angle graphene. But none of these experiments tell us which symmetries are being broken. They always tell us the number of symmetries that are being broken, but never exactly what the isospin degeneracy of the system is. And so this is really holding us back. We would love to know something about these insulators, particularly from a much more precise point of view. And we find that actually using atomic scale spatial imaging using the STM is a really wonderful way to do this. It gives me an enormous amount of insight in order to identify the symmetry broken nature of many body ground states in magic angle graphene. Instead of just saying that it is symmetry broken, I can tell you what the symmetry breaking is. So we perform these experiments at high temperatures and millikelvin temperatures for the past 2 years, and I'm really excited to show you some of these results that we've accumulated over that time. So we'll start out by talking about what we see on the atomic scale, and then we'll extrapolate at later parts of the talk to things that we see on the Morey scale. So here I'm showing an STM topograph, a low bias STM image of just a single AA site in magic angle graphene. You can see the honeycomb lattice of carbon atoms in near the AA site, where the graphene layers are locally commensurate. And then as we move to one of these AB or BA sites, we see a triangular lattice indicating the local Bernal stacking of the graphene. So this is at a density that is parked inside the flat band, but there's no gap at the Fermi level. This is just a flat band, the Van Hope singularity at the Fermi level. But when we lower the chemical potential through the flat band to half filling, we impart insulating behavior on the sample, and we find that images show very different behavior, that they show this tripled unit cell that modulates very rapidly across the Morey superlattice, which we call the R3 pattern. The R3 pattern is this atomic scale wave function pattern in magic angle graphene. It breaks translation symmetries because it triples the unit cell in a √3 by √3 reconstruction over top the graphene lattice. And it seems to break rotational symmetries in many sites where the local rotation symmetries of graphene should be preserved, like A or AB sites. So this is a really complex pattern, but one really great insight is to think about this in Fourier space, because we can analyze the wave vectors which are being captured by this R3 pattern. So here I show Fourier transform of a much larger image than this, something like 50 by 50 nanometers, where you can see these peaks labeled in black are just the Bragg peaks of graphene associated with the momentum vector G, the lattice of graphene. And then we have this subset of 6 peaks inside, which we call QIVC. These are indicating a longer wavelength, the tripling of the unit cell, so a √3 distance longer than the Bragg peaks. They're rotated with respect to it because it's on the graphene lattice, and they indicate intervalley coherence because they're associated with the K vector in momentum space. So the K vector is the one that takes me from K valley, valley K to valley K prime. So this indicates that this signature is unequivocally telling us that intervalley coherence is present in this state at nu equals -2. Doing this experiment a little bit more carefully, we find that in spectroscopy, as a function of density along the y-axis and energy along the x-axis, we'll start by looking just at this center line here, where we can look at gapped phases of matter. So up here, we see this high density of states feature, this yellow peak here that pins to the Fermi level as I pull electrons out of the sample, and then it opens and closes at the Fermi level into this deep suppression, this gapped phase, which is the nu equals -2 insulator. So taking images in the Van Hope singularity in the gapless region, we find that the graphene lattice is seen in both filled states and empty states, and the F of T of these regions shows only the Bragg peaks of graphene, the top layer of graphene. As we sweep the chemical potential into the gap phase, we see continuously that the R3 pattern onsets at all places in the Morey superlattice across every region, and concomitant with the appearance of a set of inner peaks, which we call QIVC, and some higher replica peaks, 2 QIVC, because of the dominance of the R3 pattern. So this is a really important feature of the R3 pattern, is that it's strongly associated with gapped phases of matter. Particularly, I'm showing you here at the nu equals -2 insulator, but we see it in all these gap phases that I show you here. So the correlated insulator at +and -2, at +3, we find the pseudo gap phase at +2 plus delta, and the superconductor just below nu equals -2, all show robust R3 patterns and have shown it in many devices. So This is saying that all of these phases, correlated insulators, pseudogap phases, and superconductors, are all IBC ordered phases, but they seem to have different types of IBC order because the exact R3 patterns that we see in these different phases in the same location can be quite different. Moreover, there's a lot of complexity of this R3 pattern because it varies greatly as a function of position within the Moire superlattice. So here I'm showing a much larger STM topograph, a crop of a 30 by 50 nanometer from a 50 by 50 nanometer cumulative, where we have atomic resolution in all of these areas, and you find that the AA sites show tripling of the unit cell with nematicity, whereas bridge sites look kind of nematic in a different direction, but it depends on which bridge site you look at. So this one's nematic in the same direction as the AA site, and then even places like this AB or BA site where the R3 pattern appears to be essentially absent. So this is a lot of complexity to this pattern that prohibits us from making some kind of broad sweeping claims about the observation of this R3 pattern. Particularly, it not only changes within the Moire unit cell from different places within this single unit cell, but it also changes subtly between equivalent sites. If you look at the R3 pattern closely at the AA site here, even though there are no impurities around, it seems that the atomic scale patterns are not quite the same. But so these are difficult to handle, but the one that really had us scratching our heads was that the R3 patterns change greatly between samples. So if you look at a different sample with a different twist angle, with a different strain value, with a different slight mismatch of the edge-bend alignment, the R3 patterns themselves are completely different in the different areas. So this really thwarts any ability to make some sort of broad sweeping claims other than the R3 pattern is always associated with these half-integer insulators, the U equals plus and minus 2 insulators. So with all this complexity, I think that we quickly came to the realization that we would need to start classifying these using a new analysis tool that was particularly based in symmetry, because symmetries would be robust against a lot of the complexities that we see in these samples where the R3 pattern varies greatly as a function of position in the Moire. A symmetry-based analysis tool could start with the data. We could look at the data and analyze data, local symmetries of the R3 pattern, and derive principles that may be robust across samples. And particularly, a symmetry-based analysis tool will be model-free. That in such complexity and in a space where there's so much data and it seems to change very rapidly as a function of sample parameters, we don't want to make any assumptions about the ground state until the very end, where we may compare to theory, but to derive as much information as we can directly from the data without making any overarching assumptions. So the analysis tool that we came up with in close collaboration with Mike Zolotel's group, so Tomo and JP and Mike, together we came up with this symmetry-based analysis tool, which derives a series of local order parameters which characterize the symmetries of the R3 pattern on the graphene lattice. So the complexities that you see on the Moire scale kind of converge or are easily disentangled if we just take small regions of the R3 pattern. This 2 by 2 nanometer region where the R3 pattern is roughly homogeneous. That we'll start from here and to derive some understanding of the R3 pattern locally, and then we'll move this little window across the Moire superlattice and see how these symmetries change as a function of position in the Moire superlattice. So starting with this 2 by 2 nanometer region, I argue that nearly all of the information in this image is either redundant or it's irrelevant to the problem here of classifying the symmetries of the R3 pattern. This is best seen in Fourier space, where we take a local Fourier transform of this small image here, which is produced here for their magnitudes, but I'll remind you actually that the FFT is a complex value function. And so with the FFT, we have the complex value magnitude and then the complex phase associated with every peak in the R3 in the Fourier transform. There are a lot of subtleties, making sure that this phase is well defined. I will refer you to the paper for all of this, the supplement. I will not discuss this for right now. Just assume that this function is well defined and that it is comparable in different locations in the Moire superlattice. So here we have the FFT, and we find that actually if we're just interested in discussing the R3 pattern, we don't even need to discuss the Bragg peaks, and so we can project them out, and we can limit our search from 12 peak value complex peak values to just 6. The second operation that we'll perform is a little more subtle. It comes from a fact about the FFT that says the values of the FFT of a real valued image, something like this real valued STM topograph, the values of the FFT at vectors k and minus k are actually not independent. They're related by complex conjugation. And so if you have one, then you know the other by complex conjugation. This helps us limit now our values from six different FFT peaks to down to 3. So these 3 peaks are a significant reduction of the information that we had in this STM topograph, but they still capture all of the symmetry properties of the R3 pattern in these 3 complex numbers. So at this point, what we may be enticed to do is actually to just use each of these peaks as a local order parameter. We know that when there's no R3 peaks, when there's no R3 pattern, there are no IVC peaks, and so all of these values will be 0. And once we have an R3 pattern, these peaks will turn on, and they will take on non-zero values, non-zero complex values. To be a bit more precise, what the pipeline would look like was if we divided up our STM image into a set of small STM topographs, like this 2x2 nanometer. We perform the FFT analysis. We project out all of the unusable information, the irrelevant information, and then we cast into a new basis, devised such that each basis element only has one of the FFT peaks scaled by a single unit in magnitude and a complex phase of 0. So this basis vector would be multiplied by a new complex number, which we call the local order parameter, in order to match the FFT peak that you see in real images. And then we would track this complex prefactor as our local order parameter. So this would work for each one of these. You can clearly see that this is a spanning basis set for projected FFTs like this. This will cover anything that we see in experiment as long as it's always described by this FFT. But there's one really major problem with this, and it's the fact that these local order parameters have less symmetries than the graphene lattice. Particularly the C3 symmetry of the graphene lattice is not preserved in these local order parameters. C3 symmetry about a hexagon center leaves the graphene lattice invariant, but if a state itself breaks C3 symmetry spontaneously, we would never be able to tell, because these local order parameters under C3 rotation of the STM image, the FFT has its peaks permuted. So under 120-degree rotation, Q1 will rotate into Q2, Q2 into Q3, and Q3 into Q1. And so when we rotate this this basis vector, Q1 will rotate into Q2, which will scramble the information among them. So again, together, all of these together will have C3 symmetry, but each of the local order parameters individually do not have this intrinsic symmetry encoded. So the upshot of this is to choose a different basis. Instead of picking one value of the FFT, one peak of the FFT individually, you choose linear combinations of them where their magnitudes are all the same, but their phases have different windings, which again form a complete basis for projected FFTs like this. But these have encoded C3 symmetry. Another way of saying this is that the graphene lattice would be invariant under C3 rotation, and this forms an eigenbasis of the C3 operator. A third way to say this, if you're really well versed in group theory, is to recognize that these are irreducible representations of the C3 point group. This is all saying the same thing. This is a nice basis to choose, and particularly plotting decomposing STM images into these sets of order parameters will allow us to say with a certainty that the state breaks C3 symmetry, because we know that each one of these has C3 symmetry encoded into its definition. So we're at the point where we can derive a lot of physical intuition from taking each one of these basis vectors, which are multiplied against a complex number to give us that local order parameter. We'll take each one of these basis vectors and inverse Fourier transform and convolve it back with the graphene lattice to see what do these types of patterns look like. So when we do so, we find actually that they all represent R3 patterns. They all are tripled unit cell, but they're tripled unit cell centralized on different high symmetry points in the graphene lattice. So IVC bond is named such because it's a tripled unit cell, but it has high conductance centered on the carbon-carbon bonds of the top layer of graphene. Likewise, IBC site A and IBC site B are tripled unit cells that are centered on the A or the B sublattice of graphene. So this gives us all the intuition that we need that the type of order parameter that is non-zero measured by these three that we've given the definitions for will tell us the R3 pattern is centered on these high symmetry points in the graphene lattice, but the complex phase factor will tell us something different about these local order parameters. So one more time, the local IBC order parameters capture all of the transformation properties of the R3 patterns because they are invariant under the symmetries of the graphene lattice. To give a bit more intuition, when we talk about one of these IBC order parameters, this is a complex phase, a complex number multiplied against that basis vector, which gives us its magnitude, tells us the intensity of the R3 pattern on the bond sites of graphene, but its complex phase will actually tell us where is the conductance centered in this new tripled unit cell. So now we're telling you that magic angle graphene has a tripled unit cell, but we have this new sublattice degree of freedom within the tripled unit cell where the conductance for the complex phase factors of 0, 120, and 240 all look very similar, but the ring of conductance seen in this tripled unit cell is centered on different hexagon centers within this new unit cell. So the complex phase factor is effectively telling us what is the shape of the R3 pattern within the new tripled unit cell. Although all of these three show tripled unit cells, they're all bond-centered. They can be distinguished in our local order parameter analysis. Likewise, if we look at IBC site A and site B and just modulate the complex phase of these parameters, we find that they all show tripled unit cell. They're all site A or site B polarized, depending on which one we've chosen, but they're peaked at different high symmetry points in the new Kekulé unit cell, in the new tripled unit cell. So again, 0, 120, and 240 all look very similar, but they're peaked at different A sublattices within the new tripled unit cell. So this gives us all of the intuition that we need. We're going to plot these local order parameters that give us the shape and type of the R3 pattern as a function of position in the Moiré superlattice, as a function of density, and learn an enormous amount about the correlated phases of magic angle graphene. So to get us started, let's look at just an STM topograph, a low biased image of an AA site in magic angle graphene at nu equals -2. This is a gapped insulating phase at millikelvin temperatures where the R3 pattern varies very significantly as a function of position in the Moiré superlattice. We'll take this STM topograph, divide it up into these tiny little local STM topographs, and then Fourier transform them and perform the local order parameter analysis to produce pixels in these local order parameter maps. So these are the same field of view now plotted in IBC total, which is the sum total of all of the IBC types, essentially where this is now proportional to the strength of the R3 pattern in the field of view, where white is most intense. And then IBC bond, IBC site A and site B are the ones that I've told you about, where the brightness of these pixels denote the strength of that type of R3 pattern, and then the color represents the complex phase, the shape of it inside that new Kekulé unit cell. So you can see that the R3 pattern is modulating very rapidly on the atomic scale, or on the Moiré scale, and that's exactly what's being captured by the colors in these complex order parameters, is that these are kind of coming and going and changing their shape all rapidly on this length scale. It's almost impossible to tell what's going on if you just look at one single AA site. But the real key to this experiment was to push on the device fab front to really isolate the last thing separating us from really ultra clean devices in magic angle graphene. A couple of months of hard work has paid off in the fact that we can now produce devices that where we can find 100 by 100 nanometer regions very easily of magic angle graphene, where we can now take these local order parameter maps across many Moiré wavelengths. So we'll analyze the R3 pattern as a function of position across many unit cells and see how the atomic scale patterns change on the Moiré scale. So performing this local order parameter analysis now on a 50 by 50 nanometer region, we first analyze what is the strength of the Kekulé, the atomic scale Kekulé, as we modulate our position within the Moiré superlattice. And we find a global ordering of the R3 pattern intensity. So we can find that white, the most intense regions here, are around the AA sites, as well as these kind of bridges between these AA sites. But we find deep suppressions, almost zero strength of the R3 pattern at these two dark nodes here, which are very close to AB and BA sites in the nu equals -2 insulator. These are salient features of the nu equals +or -2 insulators. In addition, when you look at one of these complex order parameters, you find that actually this state that is imparted at nu equals -2 breaks Moiré translation and rotation symmetries. We see this stripe-like feature where the amplitude is Moiré periodic, but the complex phase of this order parameter winds across the sample. This is easiest seen if we look very closely at each AA site, where we find that the complex phase is roughly constant around this AA site, but then rapidly jumps by about 120 degrees between neighboring stripes. So this is phase-sensitive information derived from the FFT, but this is information that we could never derive if we just used the amplitude information or just looked at the patterns, because we really needed this complex order parameter analysis to do the proper decomposition into the irreducible representation basis. At first, a lot of these maps look very complicated. There's a lot of features that change very rapidly as a function of position in this state. But one way to analyze this, to kind of make sense of a lot of this complexity, is to remove a phase background, to remove a linear gradient from this IBC order map, which is physical, but will reveal many features that are not associated with the linear phase gradient. So we, for understanding purposes, we remove a linear phase gradient. Again, this is a physical gradient that we see as isolated at nu equals ±2, but we remove it to see that actually the features in these order parameter maps are very simple. That it seems to be a lattice of vortices and anti-vortices, phase windings of the complex order parameter, as seen in this zoom in. So here I'm plotting this quiver plot where the arrow direction denotes the color of the order parameter, the complex phase of that order parameter. And you can find phase windings around the singularity of 2 pi or -2 pi around these specific points in the Moiré superlattice that are very close to deep suppressions in the Kekulé strength. So essentially, the idea is that the Kekulé strength, or the R3 strength, is going nearly to 0 in certain places near the A and B sublattices, and that all of the phase factors, in fact, IBC bond, IBC site A, and site B all have the same chirality winding around that singularity. So to kind of summarize, the typical features that we see at nu equals ±2 are these Moiré periodic IBC total plots with these 2 deep suppressions in the strength of the R3 pattern per Moiré unit cell. We find that the complex order parameters like IBC bond A and B all show these Moiré scale stripe phases that break Moiré translation as well as rotational symmetries. And we find a Moiré scale lattice of vortices and anti-vortices upon plane subtracting to elucidate these features that are all centered very close to these deep suppressions in IBC total. So at this point, we have an enormous amount of information about the isospin degeneracy and the real space modulations of these quantum textures, and we can run these order parameter analyses on simulations of local density of states of a series of candidate ground states that are all relevant at nu equals ±2, and then compare the maps. So we'll start with a discussion of the candidate ground states and then move to calculations of those. The best way to think about a lot of these candidate ground states is to start with a toy model, and the one that many people start with is this so-called chiral model. This is derived from the Bistritzer-McDonald model, and it's kind of an idealized model for magic angle graphene, which admits a series of flat bands. They're perfectly flat bands, and they're 8-fold degenerate for all of the degrees of freedom of the electrons in the system. So we have a 2-fold degeneracy for the valley degree of freedom, a 2-fold degeneracy for wave functions centered on the A or B sublattice, and a 2-fold degeneracy for the spin degree of freedom. So the chiral model says that all of these flat bands have 0 dispersion, they're all at the Fermi level, they're all degenerate with one another, and they're all related to one another by symmetries as split into these so-called Chern sectors, where 4 of them carry a certain kind of Berry curvature, and the other ones carry the time reversal conjugate of the Berry curvature. So here, the degrees of freedom that are natural in this chiral model are Ka, K prime B, Kb, and K prime A, where Ka and K prime B are related to one another by C2 symmetry. As I rotate the sublattice, I also rotate from K to K prime. Ka and K prime A are related to one another by time reversal symmetry. I don't do anything to the sublattice, but I rotate I time reverse the valleys into one another. And then Ka and Kb are related to each other by a composite time reversal and C2 symmetry. So the name of the game is to start with some sort of toy model like this, and then at nu equals plus or minus 2, we need to fill 2 of the 4 given degrees of freedom in order to produce an insulating phase. So these are effectively generalized Chern ferromagnets. These are Chern bands that we're filling, and we're going to fill a subset of these bands. So a really obvious way to do it is to polarize into the one Chern sector and just occupy the 2 degrees of freedom given to us. So something like Ka and K prime B. This Chern polarized state breaks time reversal symmetry spontaneously, but it protects C2 symmetry and would emit a quantum anomalous Hall effect. So this is ruled out by transport experiments, but states that can't be ruled out by transport experiments are things like the Valley Hall and the Valley polarized candidate states. So Valley Hall consists of preserving time reversal symmetry while breaking C2 symmetry, while Valley polarized states involve breaking C2 symmetry, breaking time reversal symmetry, but preserving the composite C2T symmetry. So all of these states are consistent with what is seen in transport experiments, but none of these states well, these 2 states were, but none of these states are consistent with our observations of an R3 pattern, because the R3 pattern is a smoking gun signature for intervalley coherent order. So these candidate states are now all ruled out decisively by our imaging experiments at plus or minus 2. A series of candidate insulating states at nu equals plus or minus 2 that are intervalley coherent include things like the Kramer's intervalley coherent state, or so-called KIBC state. In numerics, this is believed to be the leading theoretical candidate and is predicted by many people to be the most likely ground state at nu equals plus or minus 2. This, instead of having the Chern block spheres pointed out of plane like an Ising type configuration, these are like XY configurations where the Kramer's intervalley coherent state breaks time reversal symmetry, but it preserves a composite time reversal times a Valley rotation, which gives us this anti-aligned XY configuration in block sphere space. So that's the Kramer's time reversal symmetry, but this state is predicted by these authors not to show an R3 pattern. This is the Bernavig group and the Zolotel group, which is decisively ruled out by our experiments, that we do see an R3 pattern in every nu equals plus or minus 2 insulator, and so it cannot be this leading candidate ground state. 2 other candidate ground states that are relevant are the so-called time reversal symmetric intervalley coherent state, or the TIBC state. This is thought not to be theoretically competitive due to numerics, but does indeed have an R3 pattern. It preserves kind of time reversal symmetry upon exchange along the diagonal. And it's kind of a blander cousin, or a simpler cousin of the Kramer's intervalley coherent state. A third candidate is the so-called incommensurate Kekulé spiral state, which I'll focus on for much of this talk. It's kind of a very flavorful version that is expected to be stabilized in the presence of moderate strain, which is seen ubiquitously in magic angle graphene devices. It preserves time reversal symmetry. It breaks Moré translation symmetry, but it preserves Moré translation symmetry times a Valley rotation. So it will form these stripes of similar IBC ordered phases, but when you move to a nearby stripe, that stripe has a different intervalley coherent complex phase. So this is actually the phase that we'll focus on right here, because it shows many features that are strongly resembling our observations at plus or minus 2. So this family of states, one of them is chosen to be calculated in local density of states as a function of position, and then we run the local order parameter analysis on that calculation and compare directly to the same procedure run on experiment. And we find that IVC total, the strength of the R3 pattern, is Moré periodic in both. In both, we see these deep suppressions near the A and B AB and BA regions of the Moré superlattice. When we look at complex ordered local order parameters, we find that both experiment and theory show these stripe-like phases. In the IKS state shown here, this complex phase winding is exactly the IKS translation vector that is predicted by theory. And in fact, when we plane subtract from both of these order parameters, we find a lattice of vortices and anti-vortices that look very similar. So there are many features of experiment that strongly suggest that IKS states, this family of states, are the most likely ground states at nu equals plus or minus 2. Really kudos to these authors here, these theorists who predicted this state before seeing any of our results. So I've told you a lot of salient features of the nu equals plus or minus 2 states in typical devices here. So parking the chemical potential at nu equals minus 2, you find stripe phases in complex order parameters and a lattice of vortices and anti-vortices. I call these typical samples because they're typically seen to show gapless charge neutrality points, that there's no insulating phase here, with the exception being if the device is aligned to HBN substrate. This encapsulates nearly all reports in transport and compressibility and all reports in spectroscopy, but we find a few regions of these devices that are really rare, but they're at ultra low strain, and they seem to show gapped charge neutralities, which we can isolate to be a result of interactions because we can see every atom, so we know the devices are not HBN aligned. We can see that these samples show gapped insulating phases because they're convolved in spectroscopy with Coulomb diamonds associated with insulating phases. So we're very sure that this is not an HBN aligned device, and yet it still shows a correlation-induced gap at charge neutrality. We probe the nu equals -2 insulators in these devices, and we find that these states show very different symmetries than the IKS order seen in and ±2 in typical devices. So instead of stripes, we see that complex order parameters like this are more aperiodic, where IBC bond is effectively featureless. And when we subtract a plane, there are no associated IBC vortices and antivortices in this complex order parameter. We find that a lot of these features look very similar to TIBC, but not all of them, especially the global features of this state seem to deviate from predictions of the time reversal symmetric intervalley coherent state. So here I'm showing a low bias topographic image and calculation of the local density of states in TIBC compared to one another at the center of an AA site. And you find that these six-fold star-like patterns are reflected in both of these images, which show that the local density of states in the AA site looks very similar between experiment and calculation. Indeed, if we look at the local order parameters, IBC bond, in experiment and calculation, they look kind of broadly similar, that they're more aperiodic and they have kind of a flat phase across the entire field of view. But particularly when we look at complex order parameters like IBC site A, when we plane subtract, we find a number of IBC vortices and anti-vortices that are specific to IBCA, so we don't label them with these out-of-plane or in-plane vortex labels. But in the calculation, we find vortices that appear at high symmetry points in the TIBC state, which under changing the order parameter from site A to site B, this changes the definition of the order parameter and changes the chirality of these according to how these order parameters transform under C3 symmetry. So these are expected because the TIBC state is C3 symmetric, and it appears that we don't find these types of features, these vortex features in experiment. So although definitely not IKS order in this ultra low strain limit, it seems locally to be very similar to TIBC, but globally there may be something a bit different. Finally, I want to talk about how we use these order parameter analyses to probe superconductors and pseudogap phases at nearby densities. In transport experiments and scanning tunneling spectroscopy experiments, when we dope these insulators, we find unconventional superconductors, and we'll find that all of these states are intervalley coherently ordered, but they show different types of order parameter maps. So here's some spectroscopy at millikelvin temperatures as a function of density, where right here at the Fermi level, we see this blue zero conductance feature, the correlated insulator gap that opens and closes at the Fermi level, and then reopens into a new pseudogap phase, which closes and reopens into a correlated insulator at nu equals +3. So parking the chemical potential first in the nu equals +2 gap, and imaging, we find many salient features of the ±2 insulators in typical devices. We see these deep suppressions at two places in the Moire superlattice in Kekulé strength. We see it's a stripe phase, and we see upon plane subtraction a lattice of vortices and antivortices. When we dope the system out of this insulator, we find a complete resetting and the emergence of new IBC order in the pseudogap phase, all the way persistent to nu equals +3. So these deep suppressions go away in the Kekulé strength. The stripes turn into a kind of a broadly flattened background that the gradient points in a different direction than these stripe directions. And we find that the vortices and anti-vortex configuration is completely different, absent in these correlated configurations. So this is signaling that new IBC order emerges in this pseudogap phase. It seems to be persistent all the way up to nu equals +3, and we see something very similar in the lower flat band, where we find that there's an insulating phase at nu equals -2, deep suppressions in Kekulé strength, the stripe phase in IBC vortex anti-vortex lattice, and then when we dope into the superconducting phase at nu equals -2 minus delta, we find resetting of the IBC Kekulé strength, and we find this linear phase background that points in a different direction, and the resetting of all IBC vortices and anti-vortices. So the main experimental result from this paper was that high-resolution STM measurements enable us to image the many-body wave function of magic angle graphene, and images of this wave function tell us precisely what the complex symmetry broken order is in many of these states, with many salient features related to theoretical proposals, particularly at nu equals plus or minus 2. So with these last couple minutes, I want to tell you about some conclusions and outlook from this paper. I'm really excited about how our paper stands in this emerging field of Moire flatband physics, because it's told us a lot about some of these ongoing puzzles in magic angle graphene that we hope will inspire new theories for the insulating phases as well as the superconducting phase. So particularly, I showed you this discrepancy between the insulator order parameters and the superconductor order parameters in transport experiments where magic angle graphene is held very close to a graphite backgate or is proximatized by tungsten diselenide. We knew that the insulators were more fragile to screen electronic screening, but the superconductors persist in the presence of screening. Indeed, Pablo's group also showed us that in certain devices, when you apply a small magnetic field, you can kill superconductivity and have the insulating phase impart in the same region of the phase diagram, signaling all of this is consistent with competing orders nature to these phases. So the insulator and superconductor are seemingly derived from different orders, and they compete for phase space in this diverse phase diagram of magic angle graphene. So our study shows that they are competing orders. They're both intervalley coherent orders where atomically they look very similar, but seemingly globally they show some sort of different IBC order, the insulator being very similar to the incommensurate Kekulé spiral order, and the superconductor being something that we don't have a name for yet. And so I would love to be able to understand what is this order that we're seeing at in the superconducting phase, and why is this type of IBC order conducive to insulating behavior, whereas this type of IBC order is conducive to superconducting behavior in these devices. Moreover, our STM images of the configuration of magic angle graphene with respect to its underlying boron nitride substrate show that in devices in the ultra low strain limit, where we can image every atom, and we can see that it's not aligned to the underlying boron nitride substrate, show very different phenomenology than typical devices. So here, this STM image, this order parameter map came from a device that we saw was twisted, or had an interlayer strain of 0.03%. which a really extraordinarily small amount of strain seems to have opened up a gap at charge neutrality, as well as displaced the incipient IKS order at nu equals -2 in place of what seems to be locally very similar to TIBC. So I think this is really amazing that it seems that we knew a lot more about how magic angle graphene was going to work in this strained limit, and in this nearly idealized limit, it is still not the KIVC state that imparts. It's something different and possibly something that we haven't predicted yet. So this is really signifying that either there's some oversimplification of this main model, the Bistritzer-McDonald model that we all start with in understanding these insulators. I would argue, or I would invite you to look at the reference from Kang and Vafek from PRB this year that discusses how this model may be oversimplified in current studies. Or we need another starting point entirely. That if we keep starting from the same point and we keep getting the wrong answer, I think that we need to revisit the basic degrees of freedom or the basic assumptions of our theoretical models in order to arrive at this correct insulator ground state. Finally, this STM measurement gives us a lot of interesting perspectives in new imaging experiments for the future, particularly in correlated electron systems. So I think at the beginning of this field, we discussed magic angle graphene as being a possible model platform because it had so many interesting correlated phases. It had this unconventional superconductor. It's all gate tunable via electrostatic gating. And so we would be able to do very, very well-controlled studies as a function of density, temperature, magnetic field, all in the same area with the same twist angle and the same strain. So I think that this study really shows that that dream is really possible, because this experiment that we discuss where the insulators and the superconductors all show very different R3 patterns, but in the same area, if I can modulate the carrier density, I can do very well-controlled studies. This really elucidated what the global order of these states were, and could never be done in a system where adding dopants, chemically doping enveloping a system would induce different disorder potentials in different devices. So a sample-to-sample variation would be the dominant source. So I look forward to seeing how we can use this model platform to do many more studies that would be seemingly impossible in a non-gate tunable sample. Finally, this many-body wave function mapping procedure that I discussed here is a highly generalizable pursuit in STM imaging experiments, as long as we move far from the quasi-particle interference limit. So we make devices very clean, fine materials that have very few or no scatterers in large fields of view, and we should be able to image the intrinsic wavelengths of the wave function in these systems, particularly correlated systems. And if this lattice is built from FFT peaks that are discrete, single peaks at single places, then this order parameter decomposition will work in any lattice geometry and will tell us an enormous about the isospin degrees of freedom, the nature of correlation effects, and the dominant symmetry breaking effects in these systems. So with that, I thank you for your time and thank the team responsible. This was an enormous team effort. I really emphasize that so many people had such an enormous say on this project, particularly Ryan Lee, Myungchul Oh, Dylan Wong, were all the experimentalists on this team under the guidance of my advisor, Ali Yazdani. We received indispensable help from the Zalatel group, particularly from Tomo and JP, who helped us produce they produced the code suite that enabled all of these experiments to be done, where we could extract local order parameters. And we thank Dimitru, Jonah, Nicola, and Andre, who were indispensable to the local density of states calculations, such that we could compare experiment to theory. Thank you.